Welcome to the lecture series on numerical methods. Currently we are discussing numerical integration. In the last lectures we have discussed about this numerical integration based on trapezoidal rule, 1 by 3 Simpson's rule, 3 by 8 Simpson's rule. And today we will just go for this numerical integration based on quadrature rule here, based on Gauss Legendre integration methods. So, first we will just go for this Gauss Legendre integration rule for 1 point formula, then for 2 point formula, then for 3 point formula, and then we will just go for error analysis of Gauss Legendre integration rule. So, if you will just go for this Gauss Legendre integration methods, basically in the beginning of these lectures we have discussed that whenever we are just representing an integration, this integration is usually written in the form of like a to b f of x. And the strict rule for this Gauss Legendre integration method is that we have to transform this integration range a to b to -1 to 1 here. So, first transformation we have to do that one, and once this transformation has been made, then we can just go for this series expansion or this linear combination of these functional values at different nodal points. So, this means that once we are just transforming this integration range a to b to -1 to 1 f of x dx, then we can just represent this as a linear combination form, that is k equals to 0 to n lambda k f of x k here. Or it can be represented in the form of like lambda 0 f of x 0 plus lambda 1 f of x 0 plus h, lambda 2 f of x 0 plus 2h, plus up to lambda n f of x 0 plus nh here. So, the approach of this integration rule is that first we will just go for this undetermined coefficient form. Undetermined coefficient form means lambda 0 is not known to us, lambda 1 is not known to us, lambda 2 is not known to us, and x 0 is not known to us, and x 0 plus h is not known to us. Even if these points are not present there, we can just consider any functional or any polynomial approximation to this integration here to get these nodal points here. So, first we will just go for this Gauss Legendre 1 point rule here, that is usually Gauss Legendre 1 point rule is written in the form of like -1 to 1 f of x dx. This can be written as lambda 0 f of x 0 here. Since we are just considering for a polynomial of degree 1 here, so that is why it is called 1 point formula here. And if you just see here, lambda 0 is not equals to 0, so then we will have two unknowns here. That are like lambda 0 and x 0 here. So, if we want to determine these values for lambda 0 and x 0, then we will just go for this approximation of this function with a exact polynomial order p. And if this is approximated with a function or a polynomial of order p there, then the error constant can be written in the form of like c equals to -1 to 1 f of x dx minus summation k equals to 0 to n here, that is lambda n or lambda k x k to the power p plus 1. Since usually we are just considering this function or this polynomial which should be, if it is order greater than p, then it will just give you a non-exact term, then we will have a error is existing at that point. And this error term, that is Rn of f here, that is usually represented in the form of like c by p plus 1 factorial f to the power p plus 1 zeta, where zeta should be lies between a and b. And if you will just go for this calculation of this coefficients here like lambda 0 and x 0 here, then making this formula exact, this means that error term should be 0. If you will just consider here making this formula exact, since already I have explained that we have to consider this formula is exact for polynomial of order p. If p equals to 0, 1, 2 up to p, it will just give you the exact solution here. This means that the 0 value we can just obtain here. So if you will just use this, making this formula exact for f of x equals to like 1 and x, since we can just consider that as 1 x square up to x to the power p, since already we have considered that this is for p equals to 1 here, function is approximated or the polynomial is approximated with a polynomial of degree 1 here. So that is why we can just consider this one I equals to 1 here or p equals to 1 here. So that is why two functions we can just consider. First function is x to the power 0, that is as 1 here, second function is x to the power 1 as x here. So if you just put these functional values for this integration here, then we can just obtain that as like f of x equals to 1 suppose, then we will have this minus 1 to 1, 1 into dx. So this can be written as like 2, this equals to, if you just put these functional values, that as lambda 0 into 1 here. So that is why lambda 0 can be taken as 2 here, and for the second one f of x equals to x here, minus 1 to 1 x dx, this is equals to 0 here, and it can be written as lambda 0 into next point f of x 0 equals to x 0 here, so x 0. So that is why we can just consider that since lambda 0 equals to 2 here, that is not equals to 0, we can consider x 0 equals to 0 here. So the total formulation for this 1 point formula, it can be represented as minus 1 to 1 f of x dx, this equals to 2 f of 0. And this error constant c can be written as, since it is just represented in this form here, so c can be represented as like minus 1 to 1. So immediate next term, if you will just consider here that as x to the power p plus 1, so x square into dx here. So that can just give you like 2 by 3 here. So 2 by 3 into this is like a c by p plus 1 factorial. So that is why this error term or Rn of f, it can be written as 2 by 3 into 1 by 2 factorial f to the power p plus 1. So f double dash of zeta here, 2 to cancel it out. So this can be written in the form of 1 by 3 f double dash of zeta. So zeta should be lies between like minus 1 to 1 here. So this is the error term for 1 point Gauss Legendre integration method. So then we will just go for Gauss Legendre 2 point rule here. If you will just discuss about the Gauss Legendre rule for 2 point form here, then we can just write minus 1 to 1 f of x dx, this equals to lambda 0 f of x 0 plus lambda 1 f of x 1 here. So 2 point means we can just consider 2 points here. So that is why lambda 0 is the first coefficient here and lambda 1 is the second coefficient here, where we can just consider lambda 0 and lambda 1 are not equals to 0 and x 0 is not equals to x 1 here, and this should be determined. To making this formula exact, then we can just consider this polynomials of order like 0, 1, 2, 3, since we will have here 4 unknowns. If you will just see here, lambda 0, lambda 1, x0, x1 are 4 unknowns here. So we can just make the formula exact for polynomial of degree 3. So that's why this function can be written as in the form of f of x equals to x to the power 0, x to the power 1, x to the power 2, x to the power 3 here. Or we can just write this as 1 x square x to the power 3 here, for which exactly this function or this polynomial approximation just give the exact value here. So if you will just use these values, then we can just obtain here like minus 1 to 1, first point if f of x equals to 1, if you will just consider 1 into dx, this equals to lambda 0 plus lambda 1 here. This implies that lambda 0 plus lambda 1, this equals to 2. If you will just use f of x equals to x, then we can just write minus 1 to 1 x dx, this equals to lambda 0 x0 plus lambda 1 x1, this equals to 0 here. Similarly, if you will just use f of x equals to x square here, then we can just write minus 1 to 1 x square dx, this equals to lambda 0 x0 square lambda 1 x1 square here, and this is nothing but 2 by 3 here. Similarly, if you will just use f of x equals to x to the power 3 here, this can be written as minus 1 to 1 x to the power 3 dx, this equals to lambda 0 x0 to the power 3 lambda 1 x1 to the power 3, this equals to 0 here again. So if you will just use these 4 equations for 4 unknowns, then if you will just do some calculations, so obviously we can just obtain these values, that is in the form of like a x1 equals to minus of x0 here, and lambda 0, this equals to lambda 1, this will just give you 1 here. So this is just a simple calculation if you will just do. This means that eliminating lambda 0 from 4.12 and 4.14 here, we get that lambda 1 x1 to the power 3 minus lambda 1 x1 x0 square, this equals to 0, and from there itself we can just get x1 equals to minus x0 here, and since lambda 0 equals to lambda 1 equals to 1 here, then we can just write here x0 square, this equals to 1 by 3 here. So that's why x0 can be written as like plus or minus 1 by square root 3, and since x0 equals to minus of x1 here, we can just consider this formula as in the form of like minus 1 to 1 f of x dx, this equals to f of minus 1 by root 3 plus f of 1 by root 3 here, since lambda 0 and lambda 1 are 1 there itself. So if you just go for this error constant here, so the error can be written in the form of like c equals to like first function minus 1 to 1 x to the power 4 dx minus, if you will just consider these functional values, that will just give you 1 by 3 plus 1 by 3 here. Sorry, this is a whole to the power 4, this is 4th power here, so that's why this will be 9, this will be 9 here. Since 1 by root 3 whole to the power 4, since x to the power 4 we have just considered there, so that's why minus of 1 by root 3 whole to the power 4 also, that both will just give you here 1 by 9 plus 1 by 9 here, and final value if you will just go for this calculation, so that will just give you 8 by 45. Therefore, if you will just calculate this error here, so error term Rn of f, that can be written as c by 4 factorial. From this like earlier formulation, if you will just see here Rn of f, this can be written as c by 4 factorial f to the power 4 of zeta here. So C is already calculated here 8 by 45. So 8 by 45 into 4 factorial. So that can be written as like 24 f to the power 4 of zeta, where zeta should be lies between -1 to 1 here. Then we will just go for a 3-point formula here. So like Gauss Legendre 2-point formula, here also if you will just write this formula as in the form 3-point formula for Gauss Legendre integration method. So likewise we will just consider first one as we will just transform this interval -1 to 1 f of x dx. This can be written as like summation of k equals to 0 to n lambda k f of x k. So that is why if you just consider 3 points here, so 3 points means we can just write this one as a lambda 0 f of x 0 plus lambda 1 f of x 1 plus lambda 2 f of x 2 here. And if you just see this equation here, that is basically lambda 0 is not equals to lambda 1 is not equals to lambda 2, or we can just consider, sorry, this should not be equals to 0, this should not be equals to 0, this should not be equals to 0 here. But all of these coefficients like x0 is not equals to x1 is not equals to x2 here. So that is why we will have like 6 unknowns we have here. Like lambda 0, lambda 1, lambda 2, x0, x1, x2. And for 6 unknowns we have to like implement this polynomial approximation up to degree 5 to get 6 equations. This means that up to degree 5 this will just provide a exact solution. So if you just consider that making this formula exact for f of x equals to 1 x square x cube x to the power 4 x to the power 5 here, since 6 different values we have to consider to get this formula exact here. So if you just put all these values, then we can just obtain these values are as like -1 to 1 for f of x equals to 1, this is a dx, this equals to lambda 0, lambda 1 plus lambda 2, this equals to 2 here. And for f of x equals to x, this can be written as -1 to 1 x dx, this equals to lambda 0 x 0, lambda 1 x 1, lambda 2 x 2, this equals to 0 here. F of x equals to x square -1 to 1 x square dx, this equals to lambda 0 x 0 square, lambda 1 x 1 square, lambda 2 x 2 square, this equals to 2 by 3 here. So similarly f of x equals to x cube, it can be written as -1 to 1 x cube dx, lambda 0 x 0 cube, lambda 1 x 1 cube, lambda 2 x 2 cube, this equals to 0 here. And if you will just consider f of x equals to x to the power 4 here, then -1 to 1 x to the power 4 dx, this equals to lambda 0 x 0 4, lambda 1 x 1 4, lambda 2 x 2 4, this equals to 2 by 5 here. F of x equals to x to the power 5, if you will just consider -1 to 1 x to the power 5 dx, this can be written as the lambda 0 x 0 to the power 5, lambda 1 x 2 1 to the power 5, lambda 2 x 2 to the power 5, this equals to 0 also here. So if you will just solve these 6 equations for 6 unknowns, then we can just obtain this coefficients for like lambda 0, lambda 1, lambda 2 and x 0, x 1 and x 2 here. So in a complete form, if you will just write this formula, that can be written in the form of like minus 1 to 1 f of x dx, this equals to 5 by 9 f of minus root 3 by 5 plus 8 by 9 f of 0 plus 5 by 9 f of root 3 by 5. This is the complete formula for this 3-point Gauss Legendre integration method. So, if you just go for this error computation, so your error computation can be written in the form of like C equals to, the formula is just providing the exact result for a polynomial of degree 5 here, then the error term can be obtained for a polynomial of degree 6 here. So, that is why C can be written as like minus 1 to 1 x to the power 6 dx minus 1 by 9 if you just write. So, 5 minus root 3 by 5 whole to the power 6 plus 8 like f of 0. So, that is why we can just write that one as a 0 here plus 5 root 3 by 5 whole to the power 6, this one, and the total value just it is just giving you like 8 by 175 here. Hence, the total error term, that is you can just write Rn of f, this equals to c by 6 factorial f to the power 6 of zeta here, that is 8 by 175 into 6 factorial f to the power 6 of zeta, where zeta should be lies between minus 1 to 1 here. This is the error term for 3-point Gauss Legendre integration method. So, the general transformation method for like interval from a to b to minus 1 to 1 can be done in a easy form, that is if you will just write this transformation x equals to pt plus q here, then when x equals to a we have t equals to minus 1 and a equals to minus p plus q here. When x equals to b we have t equals to 1, so b equals to p plus q here. If you will just combine both these equations here, we can just obtain p equals to b minus a by 2, q equals to b plus a by 2. So, the required transformation for x, if we want to transform into a b to minus 1 to 1 here, then we can just write that one as b minus a by 2 into t. The transformation basically it is just written as x equals to b minus a by 2 into t plus a plus b by 2 here. So, automatically this range, that is b to a, can be transformed to minus 1 to 1 f of x dx here. So, obviously once you are just obtaining this transformation x in terms of t here, then we can just write that dx in the form of dt. So, then you can just write this formulation, that is in the form of, if you want to find this transformation, especially you can just write this part as g of t dt here. So, t obviously if you just write here dx equals to b minus a by 2 into dt, and then you can just put it over there and you can get this integration range there. If the question is asked, suppose evaluate this integral, that is 0 to 1 dx by 1 plus x using Gauss Legendre 3-point formula, compare with the exact result, then first we will just transform this range 0 to 1 to, that is a minus 1 to 1 here, then we can just apply this 3-point formula there itself. Suppose if you will just write this integral, evaluate the integral 0 to 1 dx by 1 plus x using 3-point Gauss Legendre integration method, then the first criteria is that we have to transform this integration range 0 1 to minus 1 to 1 here. So for that we will just put here that as x equals to b minus a by 2 into t plus a plus b by 2 here. If you will just write in this form, then we can just obtain here x equals to b as 1 here, 1 minus 0 by 2 into t plus half here, and this can be written as half of t plus half. We can just write t plus 1 by 2 here, and dx can be written as like dt by 2 here, and the complete integration range, that is 0 to 1 dx by 1 plus x, this can be transformed into minus 1 to 1. So first 1 by 1 plus x, so that is why you can just write that one as 1 by 1 plus t plus 1 by 2 into dt by 2 here. So this can be written in the form of like minus 1 to 1. So 1 by 2 plus t plus 1, if you will just take out, this will be 2 here, sorry, by 2 here into dt by 2 here. So 2 can be cancel it out, so it can be written as minus 1 to 1, 1 by 3 plus t into dt here. So then if f of t equals to 1 by 3 plus t here, we can now use this formula, that has integration minus 1 to 1 f of x dx, this as like 5 by 9 f of minus root 3 by 5 plus 8 by 9 f of 0 plus 5 by 9 f of root 3 by 5 here. Since function is known to us, and directly we can put these values and obtain this functional values there. For the exact solution, if you will just see here, that is I exact equals to ln of 2, that is coming as 0.693147, but the computed value, if you will just see here, that will just give you like 0.693122. And if you will just take for this error calculation, the absolute error is like I minus I exact, that is just giving you 0.00025 here. Thank you for listening this lecture in integration in the numerical methods for interpolation and the approximation of functions in various forms. Thank you for listening.